Hi, my name is Cooper Nicholson, and welcome to my Physics 2211 Lab 2 Motion of a Falling Object report. The purpose of this lab is to examine an object in free fall and compare its position versus time graph to computational models, one with only gravitational force and one with gravitational force along with drag. This is to see how forces other than gravity will affect a real-world object while it is in motion. Based upon the data collected, the graph with gravitational force and drag was more accurate to the observed model than the model without drag. These graphs and data will be shown in the next slides, and potential errors will be discussed later in the report. The fundamental principles used in this lab report are Newton's second law, which describes the relationship between force, mass, and acceleration. This equation states that the net force is equal to mass times the change in velocity over the change in time. Later in the report, this formula is used to describe what will happen when net force is equal to 0. It can also be used to find how net force is broken down into force due to gravity and force due to drag. Gravitational force is also used here since the object is in freefall moving towards the ground, so it will be affected by gravity. Additionally, the drag force formula is used, which describes the force that is opposing gravity while the object is in freefall and in contact with the fluid air. The larger the surface area of an object, the greater the drag force on the object will be. Finally, the position update and velocity update formulas are used to help predict the motion of the object and allow the comparison of models to be done. The system in this experiment is a standard 5-star notebook with the surroundings being Earth and its air. As seen in the picture on the right, I set my y-axis to be positive going up and negative going down. Then I set my x-axis to be positive on the right and negative on the left. With these conditions set, it can be seen that my object moved in the negative y direction. My initial conditions for the observed were a position of 0, negative 0.004327, and 0 meters, a velocity of 0, and a total time of 0.668 seconds. Looking at the y position versus time graph, there is a decreasing exponential function that models the acceleration of the notebook due to gravity. For the computational model with only gravity acting upon the object, different initial conditions were set into the code. The mass of the object was set to 2.1 kilograms, and the initial position was set to negative 0.004327 to make sure both objects could have the same start point and mass. Delta t was then changed to 0.033 seconds because tracker measures each time frame in that interval. The while loop was changed to 0.668 seconds since the notebook fell for that long. Then the net force was set to be only the force of gravity, and finally the velocity update and position update formulas were changed so that the final velocity and position could be calculated. The initial conditions for the computational model with gravity and drag stayed largely the same, but the proportionality constant b was changed from 0 to 3. This is an estimate found by changing b until the model endpoint was almost the observed endpoint. The formula for drag force was also added to the code and then combined with the force of gravity to calculate the net force. This is the graph with the data from the two computational models and the observed notebook's position versus time. Looking at the observed data orange and the computational model with drag blue, we can see a similar slope and overall path. These two contrast the computational model without drag, as the graph has a much steeper slope and goes further. A potential source of error is that the drag constant in the computational model is estimated, so the points along the graph could be off by a slight amount. For example, this could have been changed the net force of the computational model and made it greater than the net force for the observed, allowing for the model to travel more distance. Additionally, there could be human error from selecting the center of mass in tracker. This is due to the notebook being hard to see and sometimes only a blur in certain frames. The what does it mean question asks if any models will reach terminal velocity. By looking at the graphs of velocity versus time, we can see that the model with drag will reach terminal velocity since the velocity is becoming constant. This means that acceleration is nearing 0 and thus net force is becoming 0. This can be explained by Newton's second law, as the force of drag will equal the force of gravity. The what if question asks what would happen to the terminal velocity if the object were to initially be thrown downwards. Since being thrown downwards can be modeled by having a starting velocity not at 0, the code was changed to have an initial velocity of negative 2 in the y component. As seen by the graph, the terminal velocity would stay the same, but the difference is that the object will reach terminal velocity faster than it did if it did not have an initial velocity. In conclusion, using Newton's second law, gravitational force and drag, it was determined that more forces other than gravity were acting upon the notebook. This can be seen by the computational model with gravity and drag being significantly closer to the observed model than the model with only gravity. Thank you.